second lecture of Kinetic Theory of Gas. Kinetic Theory of Gas. So calculate kinetic energy of 1 mole of argon at 127 degrees Celsius. The value of Boltzmann's constant, see, Boltzmann constant is gas constant divided by Avogadro number. And its value comes out to be 1.38 into 10 raised to the power minus 23 joule per mole per molecule, sorry, per Kelvin. Okay, just solve it. You have temperature, you have Boltzmann's constant, you have to calculate the kinetic energy of one molecule, 1 mole of the gas. We did two expressions in the last class. One is you can use 3 by 2 RT or you can use 3 by 2 kBT. So you just have to decide which one you will prefer to calculate kinetic energy of 1 mole. And in the same question I'm adding also calculate kinetic energy of 1 molecule. This is it. Fazil, this is the first question. Huh? That's the first numerical.
Okay, sir.
Okay, if I want to calculate kinetic energy of 1 mole. Okay, Noor? Yes, it's correct. If you want to calculate kinetic energy of 1 mole, so for 1 mole, you will use this relation. It's 3 by 2 gas constant multiplied by temperature. So it's 3 by 2 gas constant, you know it's 8.314. Temperature is 127 degrees Celsius. So in Kelvin, this will be 300, right? Always keep your temperature in Kelvin. So this much of joule is the kinetic energy of 1 mole. But instead, if I ask you to calculate kinetic energy of 1 molecule, then for 1 molecule, what you can do is you can write that kinetic energy is 3 by 2 into Boltzmann's constant into temperature. Kinetic energy is 3 by 2, Boltzmann's constant is this, 10 raised to the power 23 into 300 joules. Noor and Fazil, is it clear, both these things?
Yes, sir.
Clear.
Okay, let's do one more numerical.
Sir,
Yes.
that R by NA is the formula for KB.
Yeah, Kb is Boltzmann constant, and this is gas constant divided by Avogadro number, and
Okay.
its value is this is Boltzmann constant. So Fazil, can I raise it?
Yes, sir.
Okay, do one more numerical. Next question says calculate kinetic energy per molecule and also RMS velocity of gas at 127 degrees Celsius. So it's given that Kb, Boltzmann constant, is 1.38 into 10 raised to the power minus 23 joule per molecule per Kelvin. And mass per molecule means its mass of one single molecule is 6.4 into 10 raised to the power minus 27 kg. Solve it. You can use your calculator for calculation. It's a bit lengthy calculations. So first of all, you will calculate the kinetic energy and then you will calculate the RMS value because kinetic energy is half mv square. That v is the RMS value. Yes, answers. Okay, Fazil got some answer. Okay. Fazil, your answer is close, but Noor, you're making some serious mistakes. You're supposed to calculate kinetic energy per molecule. So kinetic energy per molecule is half kb into t because when you take r, that means it's for 1 mole. So you can keep on substituting the values. Kb is 1.38 into 10 raised to the power minus 23. Okay, you took 3 by 2. No, it's not 3 by 2, it's 1 by 2. Sorry. Yes, it's 3 by 2. Yes, it's 3. Into T, your temperature is 127 degrees Celsius. That means it is 300. So if I multiply it here, that's 1.5 into 1.38 into 300 into 10 raised to the power minus 23. So if I multiply it here, 1.5 into 3, so that's 45, 450. Yeah? So it's 450 into 1.38. So 450, that I need calculator. 450 into 1.38. 450 into 1.38. This comes out to be 621 into 10 raised to the power minus 23 joule. So
So,
Fazil was close. Yes, Fazil. I'm just a second.
so the temperature is 400, right?
127. So if I take 127 plus 273, yes, it's 400, right? 400, right? 400. I have to calculate it again. 1.5 multiplied by 1.38 multiplied by 400, it's 828. 828 into 10 raised power minus 23. It's 828
So
into
the
10. Yes.
answer which I sent was actually the VRMS speed. That's why.
Fazil, sorry, I didn't get you.
So the answer which I sent is RMS speed, not the.
Okay, the answer that you sent is RMS speed. Okay. So once you have kinetic energy, after kinetic energy, you can calculate this half m into VRMS square is 828 into 10 raised to the power minus 23. So this is half into m. Mass of one molecule is 6.4 into 10 raised to the power minus 27 into VRMS square is 828 into 10 raised power minus 23. So from here we can calculate VRMS square is, it's 828 into 10 raised power minus 23 multiplied by 2 by 6.4 into 10 raised to the power minus 27. So VRMS square comes out to be, it's 828 divided by 6.4. 258.74 into 10 raised to the power 4. So VRMS is just root of this term. 258.74 into 10 raised to the power 4. So 258 is root, the closest number is, I guess, 14. Na? The square of 14 is 240, 256. Noor?
So that's 250. So that's 258.
Yes, is it clear? Fazil, Noor?
Yes, so it's clear.
Okay, let's move on to next type of questions. Huh? The next type of questions on this is they may ask you to derive gas laws. So let's derive gas laws using kinetic theory of gas, derivation of gas laws. So the first gas law, that's Boyle's law. So you may be asked to derive Boyle's law using KTG. So what is Boyle's law? Does anyone of you remember? What do you mean by Boyle's law?
So the pressure of the gas is that inversely proportional to volume.
Volume.
It states that pressure of gas is inversely proportional to volume. Pressure of gas is inversely proportional to volume. Provided there is one condition for Boyle's law to follow.
Temperature is constant.
Temperature is constant. Yes, temperature of gas is constant. So basically, it's PV is equal to constant. P is inversely proportional to V. That's Boyle's law. You can easily derive Boyle's law using kinetic theory of gas. You know that using kinetic theory, using kinetic theory of gas, what is the expression of pressure? Using kinetic theory, the expression of pressure is 1 by 3. This was the expression rho v square.
Yes, sir.
This is pressure. It's 1 by 3 rho v square. This rho you can write as it's 1 by 3, it's m by v into v square. You can just multiply this here. PV is equal to 1 by 3 m v square. So if I say that temperature is constant, if I say that the temperature of the gas is constant, that would mean that v square bar is constant. If v square bar is constant, that means your PV is constant because 1, 3, m all are constant. That means PV is equal to constant. So pressure into volume is constant. That's Boyle's law. This is Boyle's law. After Boyle's law, you can derive next gas law, which is known as Charles' law. What is Charles' law?
Volume is directly proportional to temperature.
Volume is volume of the gas. It's directly proportional to temperature, provided your pressure is constant. It states that at constant pressure, volume of gas is directly proportional to temperature. So V is directly proportional to T. Again, to derive this law, we will be using this expression P is equal to 1 by 3 rho V square. You can write this as P is equal to 1 by 3 rho is m by V into V square bar. Just multiply it here. This PV is equal to m by 3 V square bar. So if I say this V square is proportional to T, right? This V, if I say that P is equal to constant, that means your volume is proportional to the square of velocity. And you know that if this V square is proportional to temperature, that's kinetic interpretation of temperature. So from here, you can conclude that V is proportional to T. So this is how we derive Charles' law. Okay, just note it down. Just tell me, okay, just Give me one more second. Let's drive one more gas law, then we will start. Then you will write. The next is Gay-Lussac's law. Gay-Lussac's law. Yes, Fazil, what is Gay-Lussac's law? Noor?
Sir, the number of molecules is directly
No, 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 no. This is at that is Avogadro's law.
oh
At
sorry, sir.
constant volume,
Pressure is directly proportional to temperature.
temperature, yes. Pressure exerted by gas. So you have done all these laws in kinetic theory of gases or in chemistry,
Chemistry?
Chemistry.
not in kinetic theory, KTG.
No, sir.
Directly proportional, directly proportional to temperature. So pressure is directly proportional to temperature. This you have to prove. Again, to prove this, you can use using kinetic theory. It's 1 by 3 rho v square bar is constant. You can say that your pressure is 1 by 3, it's m by v square bar. Now, since volume is constant, you can say that pressure is directly proportional to v square bar. Next, what you can say is V square bar is proportional to temperature. That means your pressure is proportional to temperature. This is how we derive this third gas law using a kinetic theory of gas. Okay, now note it down, everything. You can derive all gas laws that you have studied in chemistry using this kinetic theory of gas. Everything. Everything come from here. So should I change the slide?
Yes, sir.
Just tell me when you have written up. We'll start another topic. Noor?
One second, sir. I'm done, sir.
No, ideal gas. So Noor, what do you mean by ideal gas? When you would say that a gas is ideal?
So if it follows all the gas laws, then it's called ideal gas.
Okay, and what are the approximations for a gas to be ideal?
There is no intermolecular force of attraction between the particles,
Very good. Second one.
and the size of the molecule is negligible as compared to the space between them.
Yeah, these two are the major assumptions for a gas to be ideal. Assumptions for a gas to be ideal. We have already discussed these assumptions, right, in the last lecture. So I'm not writing it again. So, but you know that no gas is actually ideal gas. Almost all gases, not almost all gases deviate from this ideal gas behavior. No real gas fulfill ideal gas conditions. But at low pressure and high temperature, low pressure and a very high temperature, real gases like hydrogen, oxygen, almost behaves like an ideal gas. Almost behave like an ideal gas. They almost behave like an ideal gas. This is ideal. So if I show this thing in the diagram, I take pressure on x-axis, and you know that for an ideal gas, PV is equal to nRT. So I can write that R is PV by NT. I take PV by NT on the y-axis. Fazil, can you predict the shape of the graph for an ideal gas? If I vary this P, how this PV by NT should vary? What should be the shape of the graph? Fazil.
Sir, is it straight line?
Straight line parallel to which axis?
Sir, x-axis.
X-axis. Noor, what do you say?
The same thing for ideal gas.
Yeah. It's because PV by NT is a constant, right? If you keep on changing P, this R will not change. So for an ideal gas, this graph should be a straight line. This is a straight line graph for an ideal. This is for an ideal gas. But if you plot the same thing for a real gas, then you will observe some variations. You will observe many variations. You would be observing many variations. So this is at temperature T1. This is at temperature T2. So T1, and I should say this is T. This is T1. T2, this is T3. So as you keep on increasing the temperature, T1 is greater than T2 is greater than T3. All three graphs are for a real gas. So it's visible, like this is ideal, this is real gas. There is a difference between them. But as you keep on increasing the temperature, T3 is the minimum temperature, T2 is just higher, T1 is the maximum temperature. This behavior of real gas shifts towards the ideal gas behavior. So that's why I have written that at high temperature it behaves like a real gas. Is it clear?
Yes, sir.
Okay, just note it down. Then we'll do the last section of this chapter, degree of freedom and specific heat. Usually, school teachers gives more stress on degree of freedom and specific heat, but this is the most important part of kinetic theory of gas. This is the part why we study kinetic theory of gas.
Done, sir.
Okay, the next is degree of freedom. So degree of freedom simply means the total number of independent variables. If I tell you degree of freedom in terms of equations, like in maths, what does degree of freedom mean? Say you have three variables. These three variables are independent. You can give any value to any variable. That means your system have 3 degree of freedom. Means you have freedom to choose any one of the three variables. You can take any value of x, you can take any value of y, you can take absolutely any value of z. So you have 3 degree of freedom. So I haven't write any equation in x, y, and z. So if I say x equal to 1, Fazil can say, oh, yeah, y is equal to 3. Then Noor can say, oh, z equal to 6. There's no issue. You can have any value of x, any value of y, any value of z. Because there is no equation. You have 3 degree of freedom. But Noor, tell me, if I write an equation in between x, y, and z, how many degree of freedom I'm left with? Do I still have 3 degree of freedom, or my freedom have decreased?
So it has decreased.
By what factor? Earlier I have 3 degree of freedom, right? And what's the degree of freedom now after writing this equation in x, y, and z? Is it still 3? It's greater than 3, it's less than 3. What is the degree?
Because I think less than 3.
How, by what factor it's less than 3? Is it 2? Is it 1? Is it 0 now? Say, what happened when we write an equation? Uh, an equation in generic form is known as constraint. Now take this equation in some generic form. Like earlier you have 3 variables x, y, and z. You have full freedom to choose any value of x, any value of y, any value of z. So you have 3 degree of freedom. That's totally freedom in this system. Now I write an equation. I give you a constraint. I said, okay, you can choose any value of x, y, and z, but those values should satisfy this condition. I said, okay, I'm taking x equal to 2. Fazil said, okay, I'm taking y equal to 3. Then, Noor, you cannot pick any value of z. Can you pick any value of z? Are you left with any choice?
No, sir. Z should be 4.
Z should be 4, exactly. Z should be 4. Is 4 or minus 4?
Minus 4.
Minus 4. So Z should be minus. So you don't have any freedom. Only me and Fazil have freedom to choose any variable. You are not left with any freedom. So how much is degree of freedom now? Yes, Fazil. How much is degree of freedom now? 2. I can choose 2 variables of my choice. Instead of x equal to 2, I can say no, my x is equal to 0. Fazil can say no, I will take 100. The only issue is with you. You have to fix your z in a way that x plus y plus z comes out to be 1. Are you getting it, Noor?
Yes, sir. I got it now.
So how much is degree of freedom now? It's 2.
2.
Fazil, you got what is degree of freedom and
Yes, sir.
how a constraint equation decrease it?
Yes.
So this is how we write degree of freedom in mathematics. In physics, degree of freedom means the number of waves in which your system can have motion or the system can absorb energy. So I'm writing its definition. It is the total number of coordinates or independent quantities required to describe completely the position and configuration of system. Position and configuration of system. You can also define is the number of independent ways in which the system can absorb energy. And I'm writing this thing. This definition is fine. For example, so you have a point mass. It's a point mass. You know that a point mass can have only one type of motion, and that is translation. Your point mass cannot rotate, it cannot vibrate. For rotation and vibration, you need a rigid body, you need a system. If you just have a point mass, it can have only translation and motion. What type of translation motion it can have? It can move along x-axis, or it can move along y-axis, or it can move along z-axis. It can move in any direction. So how much is degree of freedom for this point mass, Fazil?
Sir, 2.
Why 2? It can move along x-axis, it can move along y-axis, it can move along z-axis. It
Then
can move in
3.
3 directions. So its degree of freedom here is 3 now. So this is how we will write degree of freedom. But instead of counting degree of freedom Physically, we will use a simple relation to find degree of freedom. That's 3n minus k, where n is the number of particles, particles, and k here is number of independent relations between particles. K is number of independent relation between particles. Independent relation between particles. It's K. K is the number of independent relations between the particles. So K is basically constraint. So you have three particles and you have one constraint. So degree of freedom decreases by a factor of 1. So once you know this thing, this expression, you can write degree of freedom for various types of molecules. Say you have a monoatomic gas. You have a monoatomic gas. Monoatomic gas means gas having only one molecule. You put n equal to 1. When you put n equal to 1, your degree of freedom will be, it's 3n minus k. Your k comes out to be 0 because there is no relation. So 3 into 1 minus 0, your degree of freedom comes out to be 3. That is your degree of freedom now. For a monoatomic gas, this degree of freedom is 3. After monoatomic gas, you can have a diatomic gas. If you have a diatomic gas, means you have two molecules now. But if you have two molecules, there is one relation also. So there is one constraint, k equal to 1. When you write degree of freedom, that will be 3 into 2 minus 1, so it will be 5. So you have 5 degree of freedom. So 5 degree of freedom means 5 types of motions. It can move along x-axis, along y-axis, along z-axis. It can also rotate about 2 axes. So 5 degree of freedom means 5 types of motion, 3 of translation and 2 of rotation. 3 of translation and then 2 of rotation. This is the degree of freedom for a diatomic gas. Similarly, you can calculate degree of freedom for a gas which is triatomic. Triatomic gas. Say you have a gas having 3 atoms. This is a triatomic gas. Now, again, in triatomic gas, you can have two options. This is one which is non-linear, and then you can have linear. This is non-linear molecule. Number is 3. How much is constraints here?
3.
3 constraints. 3 relation between the molecules. So your K is equal to 3. When you calculate degree of freedom here, it comes out to be 3 into 3 minus 3, 9 minus 3 is 6. Similarly, if you have a linear molecule, this is 1, this is another, this is third. Your n is equal to 3, your constraints is 2, your degree of freedom is now 7, I guess. 3 into 3 minus 2, your degree of freedom is 7. So these are degree of freedom. Means these type of motions your system will have. 3 translation, 3 rotation, 3 translation, 3 rotation, 1 vibration. Just note it down. Then we will see what is law of equipartition of energy, and finally we will calculate specific heat of gases.
So done.
Done. Okay. So noted this thing, na?
Yes, I know.
Yes, sir, done.
The next is law of equipartition of energy. This law actually we have derived in the last class. I just not named it. We have derived this thing in last class. We have derived na, that energy is 3 by 2 kBT.
Yes, sir.
That was law of equipartition of energy basically. Law of equipartition of energy says In any dynamical system, in thermal equilibrium, the energy is equally distributed equally distributed among its various degree of freedom, among its various degrees of freedom, and energy associated with each degree of freedom per molecule is half kBT. So this is energy associated with each degree of freedom. Yes, Noor, thermal equilibrium means temperature is constant. If the temperature is constant, then energy for each degree of freedom will be half kBT, half Boltzmann's constant into temperature. Using this law and the concept of degree of freedom, we will derive the specific heats of different types of gases. Just note it down, then we'll start the calculations for specific heat.
Sir,
Yes,
we derived it's 3 by 2 kBT, right?
yes, but when we derive 3 by 2 kBd, we consider a molecule, a single molecule, and a monoatomic molecule. That monoatomic molecule have 3 degree of freedom. So that was basically 3 into 1 by 2 kBd. That was for 3 degree of freedoms. Here I am writing for 1 degree of freedom.
Okay, sir, understood.
If you want to write this relation for a molecule having 3 degree of freedom, you will write 3 by 2 kBd. Just tell me when you have written. Can I change the slide?
Yes, sir, done.
Sure.
Yes, sir.
Now let's calculate specific heats of gases. Specific heat of gases. Let's first of all calculate specific heat of a monoatomic gas. I'm calculating specific heat of a monoatomic gas. So to calculate specific heat of a monoatomic gas, so for a monoatomic gas, to calculate specific heat, let's first write energy for each degree of freedom. Energy, sorry. So energy with each degree of freedom. With each degree of freedom. Energy with each degree of freedom is half kBt. For a monoatomic gas, you have 3 degree of freedom. So energy with each molecule, or I should write energy of each molecule. Of each molecule is 3 by 3 into half kBt. So this comes out to be 3 by 2 into Boltzmann's constant into temperature. This is energy of each molecule. Now, after energy of each molecule, you can calculate energy of one mole molecule. Fazil, how would you calculate energy of one mole molecule if you know energy of one single molecule? Yes, Fazil. I have given hint. This is energy of one molecule. Now I want energy of one mole molecule. How would you calculate that?
Sir, is it divided by
Divided by. Nah. Noor,
So multiply into one now. After
multiplied by Avogadro number, yaar. Fazil. This is for one single molecule, no?
okay,
One mole
yes.
means Avogadro number. So if you multiply Kb and Na, what you will get? Fazil. If you multiply Kb and Na, then what you will get? You will get R, gas constant. Remember, gas constant divided by Avogadro number is Boltzmann constant. This is 3 by 2 RT. And this is what we call the internal energy of gas. This is internal energy of gas molecules. So the internal energy of gas molecules is 3 by 2 R multiplied by T. This is U. So once you have internal energy, you can calculate specific heat at constant volume. You can now calculate, I should use the next slide. So now you have U equal to, it's 3 by 2, it's R into T. Now we can calculate molar specific heat, molar specific heat at constant volume. So molar specific heat at constant volume is Cv, which you can write du over dt, which is equal to 3 by 2r. If I differentiate this term with respect to temperature, this is 3 by 2r. So this is your molar specific heat, which is 3 by 2r. Now, once you have Cv, you can calculate Cp. To calculate specific heat at constant pressure, we use Maier's formula. Maier's formula says Cp minus Cv is equal to R. So you can say that Cp is Cv plus R. Or you can say that Cp is Cv. How much is Cv? It's 3 by 2R plus R. So your Cp comes out to be 5 by 2R. So you have Cp as well as Cv. You can now calculate specific heat ratio. Specific heat ratio that we call gamma. Gamma is the ratio of Cp and Cv. How much is Cp? That's 5 by 2R. How much is Cv? That's 3 by 2R. So R 2, 2. This is 5 by 3. This is the same gamma that we have used in adiabatic process. This is how we calculate gamma for an adiabatic process. Tell me, is it clear?
yes, sir.
Now you can get this derivation, for this calculation for any type of gas. You can say that's triatomic linear. The only change is in the value of F only. Just keep substituting the values of F and keep on solving it. Okay, just note it down. Then you will do it for triatomic non-linear molecule. Just tell me when you have noted.
So could you show next slide?
Yeah.
Sir, that is 5 by 2 divided by 3 by 4, right?
3 by 2. 3 by 2, 3 by 2. CV is 3 by 2, no? It's basically 2. I have cancelled it, so it's looking like 4. It's 2.
So I'm done.
And
Okay, now do one thing. Repeat it for a triatomic linear molecule. Do it for a triatomic linear molecule. Hmm. Yeah, we'll do this. Triatomic linear. Do it. How much is degree of freedom for this type of molecules?
2.
Gamma is no. Noor, no, no. You are making some mistake. Not gamma, not solar value gamma. You're using linear, na? So linear, your F is 7. Yeah, 7 by 2 is CV, right?
yes,
7.
sir.
7. It's 7. It's 7. It's 7. It's 7 by 2R. It's 7 by 2R. And this is 7 by 2R. This is 9 by 2R, na? No, that will be 9, I guess. 9 and this is 7. So that will be 9 by 7, not 10 by 7.
Yes, sir.
So that was about kinetic theory of gas. So so this is finished. There is one small definition in kinetic theory of gas, that's basically the mean free path. Let me discuss what you mean by mean free path. No, Fazal, it would be 9 by 7, not 7 by 5. It would be 9 by 7.
Yes, sir.
The next is mean free path. So basically, what mean free path means, when a gas molecules move, it does not travel in a straight line. It travels in this way. It travels a zigzag path, some sort of zigzag path. It travels, and it keeps on colliding with other molecules. So during two collisions, say one molecule here and another molecule here, during two successive collisions, the average distance traveled by the molecules is known as mean free path. So mean free path means mean free path is average distance traveled by molecules between two successive collisions. So when molecules of a gas move, they collide with each other. Between two successive collisions, the distance that the molecules travel is known as mean free path. I'm also writing the expression, although it's not required, but let's write this expression of mean free path. Pi d square p. This T is temperature. This lambda is mean free path. This d is the diameter of molecules. Is the diameter of molecule. P is the pressure. That's it. This is mean free path. Just note it down. This completes your kinetic theory of gas. Now let's come back to waves. We have to finish standing wave and beats there. Or also Doppler's effect. You have done Doppler's effect in class or not?
No, sir.
Okay. Let's finish this beats and mean standing waves first. Written?
Yes, sir.
In
No, sir.
kinetic theory of gas, the most important topic is the specific heat. So the major chances from this chapter is the specific heat of different types of gases. Okay, let's just a second.
Sir, can you show the last slide once?
Yes, yes, yes.